Okay, let's talk about our CPU. First, our CPU is based on the diagram here, and we generate our own diagram. This is our component design data path. There are 6 components. They are PC, program counter, instruction memory, ALU, data memory, value from, and control unit. The blue light here are control signals. They are and black light here are data signal or data, and black light is the instructions. In the control unit, we generate the intermediate number and the branch control signal here. And I will talk about the components. First of all is the control unit. There are 2 main inputs. One input is instruction to generate the OP code function 3.7. Another input is data from RX1 and RX2 to generate the branch control signal. And there are also other 4 kinds of outputs. They are all control signals. First of all is the read enable signal, and the second one is the write enable signal, and the third one is switch signal to control the max to 1 in our components, and the last one is the operation code to control the operation of some other components. And let's talk about the FSM. There are 5 main states, and there is an extra state, help state, and when the set signal is valid, it goes to the instruction fetch state, and the instruction fetch states go to the instruction decode state, and it decides on the output code is held, it goes to the state held, else in the B times instruction, if the branch control signal tell it to jump, it will directly go to the memory state, or else it will go to the execute state and the ALU to execute it and go back to the memory state. And after the memory state, it goes to the write back state. This is the last stage, and it finishes the write back state. It begins a new cycle to go back to the instruction fetch stage. And about the program counter registered, and we can see our simulation. So the program counter generate normally, and the instruction memory also can generate normal instructions as input goes. And talk about the ALU. The ALU in the simulation, this is the instruction. Also the test case, you can see the output is right here, and also the data memory. The data memory, we test the stored here, and we can see we firstly put this into the RS2 and we executed this full instruction. We can see the data memory exists, the data what is supposed to be, and the load also load data from the place in the memory to the register file. Also, we can see that is right for these 5 instructions, and since it's very interesting case is the low high and the low half world and the low half world on side. We can see the half world of the data is the same, but the other half world of the MSB of them is completely different, because the data here the side bit is 1, so they're different. So that's all for the simulation and the design.
So let me cover the performance and area analysis part. So first of all, CPI means cycle per instruction. normally, if CPU is designed in 5-stage pipelining, its CPI should be close to 1. Since we didn't finish that part, so our CPU will execute the instructions sequentially. CPI will be 5 exactly if we still execute each stage in 1 clock cycle. However, we improve the performance by comparing the data from the source registers in control unit and jump to the destination program counter for B-type instructions. And for example, in the second high-level test cases, and I will cover that part later, our CPU executes 76 instructions in 361 clock cycles, and the total CPI is 4.75. And the next part is about timing simulation. So we improve the timing slacks by changing lots of combinational logic to sequential logic without decreasing CPI. In other words, many data can wait for another several clock cycles in our original logic. And as you can see, the first version with clock cycle period set as 5 nanoseconds, the timing slacks are too large, and we need to increase the period to 11 nanoseconds, and the timing constraints are met. So in the final version, we still set the period as 5 nanoseconds, and as you can see, all the timing constraints are met. And compared to the first version of our first complete RISC-V CPU, we improved 5% on CPI and 120% on clock rate. As a result, we improved 131.6% performance for the total CPU. In other words, it only costs less than half of the original CPU time to execute the same program. And in the area analysis, we use a lot of lookup table and flip-flops, and the other resource doesn't cost much. Now let's talk about the high-level test cases in, well, actually in machine code, but we found a RISC-V assembly code to machine code converter on the internet. So, well, it's very convenient. So we only need to write codes in assembly and then convert it to the machine code automatically. So the first is LFSR. Well, it's similar to, well, it's the same as the midterm problem. So, but, well, normally it's pretty easy. We only need to shift left logical. So, but for the bit 0, well, it's very difficult to do it because it's the result of XOR of many types. So how to extract the value from those types, for example, from bit 15? Well, we need to shift right logical, the total register and it with 1. So the last bit will be stored in the result in the destination register, and the higher 31 bits will be cleared to 0. And we do the same to other types, and finally we do the XOR operation to the storage registers and put the result back to bit 0, and we compared it with the result from the midterm, and as you can see, it works well. So the next test case is called two-sum simulation. It's similar to the first problem on LeetCode, well, but there's still a little bit difference. So we only generate six numbers and store them into the data memory, and we generate another target number and store it to the memory, and then we need to find which two from the first 6 numbers, their sum is equal to the target number. So this is called two-sum. So first we load for the first two numbers into registers and compare the sum, and then we change the second number from number 2 to number 6, and then we do the summation and compare it with the target number for each loop. But this is the inner loop. We still need an outer loop. So there will be two loops. In the outer loop, the first number will change from number 1 to number 5. Well, because we don't need to change it to the number 6 because we only allow two different numbers to do the summation. So, and in this example, well, we will, after we find the numbers we want, we will store their index back to the data memory. And as you can see here, number 2 and number 6 is what we want. And if we haven't found that results we need, we will store like an indication, like a flag bit back to the data memory to indicate that we found nothing.
Finally, I want to talk about our future expectations. First, as we mentioned before, our total CPI is about 4.75, and normally, if CPU is designed in 5-stage papering, its CPI should be close to 1. So our CPU executes instructions in sequence, so our CPI is too high. We will design a 5-stage papering logic and hazards control logic, which can bear the hazards resulted by papering. So in that way, we can reduce our CPI. And the second, for the clock rate. The highest clock rate that our CPU can run at is only 200 MHz. We will keep optimizing the logic in order to achieve higher performance. That's all. Thank you.